we're gonna do is.
Right.
Okay, I think we can start. The first thing we're gonna do is just get a really brief introduction to the various members of the committee. So let's start with Morgan. Say it's just briefly something about the committee.
Sorry.
Tell us about yourself.
Morgan Barner, I'm the Director of Research at Tall Timbers.
Okay, now go to next. We're gonna go counter, basically clockwise.
I'm Kelly Barsanti. I'm a scientist at the National Center for Atmospheric Research.
Okay, next, Phil.
Good morning, I'm Phil Rigdon. I oversee Department of Natural Resources for the Yakama Nation tribe in South Central Washington State.
Okay, Marcella.
Marcela Lavilla, I'm an assistant professor at the University of Oklahoma. Ilka Eltonbridge, University of San Diego.
Okay, Albert.
Albert Simeoni, Worcester Polytechnic Institute.
Okay, Talat.
Talat Odman, Regents Researcher, Georgia Tech.
Hi, Derek Tesser, St. Louis University.
Hi, Tirtha Banerjee, University of California, Irvine.
Okay, Chad.
Chad Hoffman, professor at Colorado State University.
Rodman, Los Alamos National Lab.
Okay, and then Dar Roberts, UC Santa Barbara, and chairing this group of individuals. And then, of course, we have some of our sponsors. Do you want to say anything? No, you're gonna. Yeah. Okay. And then just briefly go over what our agenda will look today, and then we'll do some housekeeping. First, we're doing the welcome and introductions. And then I think the key element for today is we're going to have 3 presentations. One of them is going to be at 10:15. That's Prescribed Fire Combustion Atmospheric Dynamics Research Experiment, RX Cater, and DoD at Southeast campaigns. We're going to have another one starting at 11:15. That's the fire influence on regional to global environment and air quality, otherwise known as Fire XAQ. We'll eat food, which was during what's called a lunch. Then we're going to do Western Wildfire Experiment for Cloud Chemistry, Aerosol Absorption, and Nitrogen, otherwise known as WECAN. And then we will conclude today with discussion of future meetings, additional campaigns, and other things we'll be doing in our report strategy for this committee. So with that, Stacy, want to give us some of the ground rules?
I'm Stacy Karras with the National Academies, and I'll be serving as the director for this study. I just want to go over a couple of housekeeping items. Again, for those in the room, probably should have done this earlier, but the exit, should we need to evacuate, is out these doors to the left through the main hall, and then out the Constitution Avenue entrance. Those of us in the room will be using our tent cards to indicate we want to speak. For those on the line, if you would like to join the conversation, we invite you to indicate that you would like to speak by using the raised hand feature within Zoom. Otherwise, we ask that you remain muted unless called upon to speak. I do want to reiterate that during the Q&A sessions or the discussion portions of our agenda, we will give priority to committee members that may want to ask questions or provide comments, but we will invite those on the line or our invited guests to also participate if and as time allows. We do have scheduled breaks, but if anybody in the room needs to excuse themselves beforehand, we ask that you just do so quietly and courteously. And the same goes for those on the line. It looks like most people have their cameras turned off, but if you need to excuse yourselves from the discussion, we just ask that you do mute yourself and turn the camera off. I want to reiterate the point that this is our first substantive meeting of this committee. We look forward to an iterative information gathering process and future opportunities to engage with members of this community. So again, this is not our final opportunity to engage with any of the folks we have on our agenda today, nor is it the last opportunity to engage with others in the community. I think that's all I've got for today.
Okay. And so I think we have our first talk to deal with, which is going to be led by Joe O'Brien. So if we can start that, I think that'll be good.
All right, let me introduce myself. My name is Joe O'Brien. I'm the project leader for the Athens Prescribed Fire Lab in Athens, Georgia, part of the USDA Forest Service Southern Research Station. I'm assuming I have sharing capacity here. Yes.
Be able to
Yeah, let me. All right, let me. Am I sharing?
Not yet.
I clicked the share button and nothing's happening. This is classic, isn't it?
Was there a pop-up ask to select a window or
Negative. There we go.
Also-
All right, let's get the show on the road here. All right, so I was brought in to speak about RX Cadre and the large prescribed fire campaigns that we have been running in the Southeast for about the last 20 some years. So I wanted to touch just briefly on the long history of actually measuring fire that, you know, has been going on in the Southeast since the 1950s. And I'm not going to go that deep into history, but I just wanted to keep that context in place as, you know, as we dive into history, there's a lot we can learn from the past that we've forgotten about. So really what the focus of my talk is going to be on, you know, why and how we need to actually measure fire in the wild. So if you want to study a tiger, you can look at it in the zoo. You get it, you know, it's like a lab experiment. You could force the tiger to model its behavior, and you can see the tiger. You're going to learn a lot about the tiger yawning, but you can get the most information about how the tiger behaves in the wild, and it's actually the most interesting and satisfying kind of research. So 20 some years ago, we started this endeavor to try and build these large scale integrated fire measurement campaigns. Deep time. Just wanted to show you that this is what I used to look like, and now the ravages of time, you know, we can study that too. But we're going to begin with RX Cadre. So it was the research combustion atmospheric dynamics research experiment that began in 2007 with some discussions with the Core Fire Science Caucus, which was a little group of researchers way back then that realized that we needed to get together and advance the science to sort of build better models, understand the fundamentals of wildland fire behavior, and just do a better job on the whole of capturing this incredibly complex and important phenomena. And the first go round was in 2008, where we got together at two sites, Eglin Air Force Base and the Jones Center, to just sort of come up with a test case, sort of a test scenario where we're going to actually try and measure a fire. You know, so little fire measurements had been, you know, fire in the wild had not been well studied. And so we tried to build a little campaign that we would measure in fire, in situ fire behavior, some atmospheric dynamics, et cetera, et cetera. These built into larger efforts at Eglin Air Force Base in 2011, and then in 2012 we got some joint fire science funding to actually try and build a truly large-scale integrated project. The reality is the first RX Cadre was, can we do this? Can we get along? Do our measurements compatible? There's a lot to this that is really important that I've seen in my 25 years of doing this, that balancing these compatibilities and personalities is really important, and it's something that we don't often talk about. After the RX Cadre campaigns, they were no doubt highly successful, but there was clearly a real need for improvement. And this is how science works. You iterate and you improve. One of the things that we learned among discussions among ourselves, that while we did have an objective, if you don't have a consensus on what that objective is and where your work fits into that objective, there's not only lost opportunities, but there can be bad feelings, and that makes it less likely that you're going to want to participate in the future. So there's a lot of effort that goes into these things. You have to balance your needs and goals with others, and we realized we need to do a better job of coming up with more consensuses. this also played into just like, how do we leverage synergy? Like, we need better integration among the scientists. But the really, really important thing that we realized way back then was that we need to integrate with operations folks and build this sort of co-production concept. So these were all lessons learned, and really kind of the underlying theme in all these projects is data management, not only documentation, but just some kind of efficient and streamlined way to collect these disparate and large scale data sets together so that they're usable both to ourselves and to others that might be interested. So this was, this is really well the only time I'm going to spend on RX Cadre. After RX Cadre, there was a big push for DoD fire science to sort of improve fire management on military bases and kind of build on basic fire science as well as applications through the CERTUP and ESTCP programs. This was about a 7-year period that I was involved with these programs, and we did more than 40 operational burns at Eglin Air Force Base and Fort Stewart with a whole bunch of colleagues. It would be like the Oscars. I would have to use all my time to call out all the great colleagues that we've had working on these projects over the years. But really, one of the things that started to emerge was from my research, and I think for the greater campaign, was the opportunity for instrumentation innovation. And we really made some real leaps forward in how we can actually capture fire behavior in situ, on the ground, at high resolution, and through temporal timeframes. That's really, really important. And of course, we also kept building ideas on how do we do a better job on building these campaigns? How do we leverage multiple talents? How do we bring in the operations folks? There are a lot of spin-offs as well, with work at Tall Timbers and more work at the Jones Center, and then even local opportunities with national forests. So the end result of this effort was that we put together a white paper for CERTUP to sort of come up with an approach to combine operations and research in a way that would make it palatable to operations crews, so they wouldn't be hesitant to allow a bunch of scientists to measure their fires, but also just to streamline both the research in terms of compatibility with different projects, different measurement techniques, make sure we mitigate potential conflicts. And this was funded, and we created this thing called the Integrated Research Management Team. And so this built off of 10 years of lessons learned on many, many, many large campaigns. And what we did was we leveraged our fire experience and used the incident command system, which is this really efficient organizational scheme. And we created a seamless integration of research and operations. And it was successful in that we're speaking the language of the operations folks. We lifted a lot of logistical responsibilities off the researchers to free up their time to focus on the science. There was a built-in safety sort of network that made sure that outcomes were going to be safe for everybody involved. Just all the efficiencies that were built into this, leveraging the ICS and the sort of the approach of how wildland fire is managed operationally. And we were able to mitigate conflicts, make sure somebody's not trampling somebody else's plot, make sure that the aircraft aren't conflicting with the operations aircraft, et cetera, et cetera. And what we learned is, the innate benefit of the incident command system is its inherent flexibility and adaptability. It can expand and contract with complexity. And we really, really learned this in 2025 when we had to pivot at the last minute from a planned fire at Merritt Island for the FireSense campaign to another site, and we were able to just, roll and go. And so the Integrated Research Management Team has really been pivotal in building successful multidisciplinary, integrated, large fire campaigns. So when we built the IRMT, the first test case was at Osceola National Forest, where we just wanted to see how well it would work with a friendly audience. And so we've been burning these plots for, as I mentioned, decades, and the fire crew down there was very comfortable. And we were able to sort of do some shake shakedown runs with the principles of the IRMT. And we were very, very confident that it was going to work. We applied it at Fort Stewart at some large fire campaigns in 2022 and 24, moved over to Eglin in 2023, and we can talk about details of this stuff later. And then, as I mentioned, we pivoted from Merritt Island to Fort Stewart and brought in a new group, the FireSense folks, which added a whole level of complexity, but it wasn't a big deal. So to sort of kick off the discussion, where are we now? We've got a program that I've been using and many others in the room. I feel like I'm talking to, I've taken a lot of your slides without attribution, so I apologize. But it's a successful approach. It works both on 2 investigator campaigns on a single burn or a large multi-campaign, multi-investigator, multi-agency campaign. It's extremely flexible and effective. Some of the really important lessons learned are we have to embed science with operations, not only to have access to the fire so we can measure them and get up close and get our instrumentation deployed in advance of the burn and understand what's happening, but the feedback, the co-production, the insights that we get from the fire operations folks when we are interacting with them as peers, not in the concept of tech transfer or not in the concept of who are these pointy-headed scientists trying to tell us how to burn. There's a much more productive interaction between those using fire and those studying fire. The other thing is the more we do this and the more people get fire line experience and the more they get close to fire and see it, they get ideas, and they can then go on and advise other campaigns or just do better fire science with exposure to fire in its natural habitat. And so through the EILN, and I say we, the royal we, I'm a tiny cog in the giant wheel, but the Eastern Innovation Landscape example is how we've taken this large fire campaigns and then extended it to a new way of trying to accelerate the application of discoveries. And we don't have time to wait for the traditional sort of paradigm of make a discovery and then wait 5 years before that discovery is applied. We need to, we have a wildfire crisis. We have a real need to accelerate science to better guide wildland fire management. And so this new paradigm has emerged through these innovation landscapes, and these two are also working. And we did get a Chiefs Award for this effort, and we feel like this is an area that needs to be expanded. The test case was the Eastern Innovation Landscape, but this principle, both the IRMT and sort of these innovation landscapes, show great potential. So I try to come up with a mnemonic to help you remember my 2030. I have about 6 years of post-fire ecology experience and about 26 years of actual fire ecology experience, but I got 7 O's and a G. So in my experience, my long career, what I have observed for successful on-target campaigns, first of all, the objectives. It has to be objective driven, and the objectives have to be compatible amongst all the players. These objectives have to be clearly defined. They have to be achievable as well. That's a no-brainer, but it's really important that that's the driving principle when you organize these large campaigns. They have to be organized, and we've come up with a system through the IRMT to maximize synergy, minimize redundant efforts, minimize conflicts. The system is designed to integrate operations so that they're going to get a lot of value added from putting up with, dozens of scientists roaming around their fire. The data that and I haven't really talked about this, but the WFC data portal to me has been one of the best things to come out of these big campaigns lately. It's a really efficient way of gathering metadata, of publishing your data sets and making them easily accessible. The professionals who have designed it well, and nobody likes metadata. Nobody likes building and sharing databases as a exercise, but it almost makes it fun. Just the synergies that keep emerging, the opportunities for cooperation, co-production, ideas get developed, new sensors get built, all kinds of opportunities for innovation, cooperation, co-production. And the key thing that, those of us who have been studying fire for a long time and have been immersed in fire operations, the ability to bring fire scientists right up close and personal to the fire is critical for understanding fire. There's only so far you can get from studying the tiger in the cage or trying to model its behavior. So, it's kind of it's almost kind of a minor opportunity space, I suppose, but standing next to a fire, looking at the plume, seeing what goes into actually operating around a fire. And it's really important for being a better fire scientist. And Gemütlichkeit, I couldn't come up with an O word, but I thought this idea of working together in a comfortable and collegial environment that's fostered by something like the IRMT allows a lot more, there's a lot more space for collaboration and collegiality. And so the last pontification I'm going to take with this opportunity to address the National Academy and this esteemed panel is that some of the things that keep coming up in my experience over sort of my career is that there's this false dichotomy between prescribed fire and wildfire. If we remember that the definition of a prescribed fire is strictly related to its ignition planning, it's a planned ignition. Somebody said, I'm going to go light a fire over here under these conditions with these objectives. Wildfire is an unplanned ignition. The intensity of the fire, the size of the fire, the duration of the fire, there's some correlations between prescribed fire and wildfire, but they are not they don't emerge from the concept of whether it was a planned ignition or an unplanned ignition. And this tends to skew perceptions that, all your prescribed fires are little weenie fires that are short duration, small scale, and have kind of boring flames. And this was, when I was speaking to some of my NASA colleagues, this was a test. If you're looking at these two fires, the one with the little flames on my left, probably your right, is the wildfire, and the other one is a prescribed fire in Banff National Park in Canada. So this idea that small fires are prescribed fires, high intensity fires are wildfires, we just need to move away from that. It's not useful. And we remember that if we have a program in place, there's this realm of fire, and this is just focusing on fuel moisture. The whole ability for wildland fire to burn, occurs across a spectrum of, in this case, fuel moisture. So you go from barely skunking around, burning only in grass because it's so moist, to everything is consumed to white ash. A prescription window can slide anywhere on that sort of spectrum. And so we just need to move away from the idea that prescribed fires aren't able to provide useful information for informing wildfire science. So let's get over that. The other thing is prescribed fires, because they are planned, and this is a no-brainer as well, obvious point, you can get out in advance of the fire. You can measure things that you think are going to be important in advance of the fire. You can wait for the right prescription window to get the results that you want. But the most important thing is you have access to the fire. Working on wildfires is very difficult. That's not the objective of a wildfire, is public safety and protection of property and firefighters. Adding a scientific sort of objective to that is difficult, often impossible. So we can exploit prescribed fire for science. It's amenable to science, and we can still use it to inform wildfire behavior. And I'm just going to end too with sort of where one of the things that I think is going to emerge out of something like the EILN is that we're going to end up with a more unified version of a wildland fire prediction model, where we have fire behavior integrated with smoke production, integrated with fire effects, allowing even other predictions to emerge, community assembly, things like that. So National Academy, this is what we need. We need a unified model of wildland fire. And to go back in history, this is James Furman's classic burning question slide. from probably 20, 25 years ago. I'll end my rant here and open it up to the panel, the esteemed panel, for comments, abuse, questions. And let me get going there. Okay.
Okay, well, I think we're going to do what we've been doing. So we'll have questions. If you want to ask a question, please turn on the microphone for our current set of speakers. And so if you can start, I think that'd be good. So who wants to start asking questions? Morgan.
Hey, Joe.
Hey,
This morning and yesterday, we were talking about what the campaign is, that the term campaign.
Okay.
And you've been involved in several. And this morning, what we were digging into was the deliverables from the campaigns. And you
Okay.
nailed that. You sort of gave us a slide almost on it, you know, that it, there's the paying attention to the objective. And so delivering on that objective in some very, you could say, some hard ways, you know, like we learned this, or we wrote this many papers, or whatever those individual metrics are. And then there were also some soft metrics, and you had a picture of, you know, a first-time scientist, you know, being engaged in prescribed fire. But could you talk a little bit about that, you know, the sort of, what's the delivery on these campaigns? What do you see in that spectrum? Because it's something we're trying to define, you know, what is a campaign, what's not? What do you get from them, and what do people get? You know, is it 8 studies that are unrelated, or is it this piece? So if you could just speak to it, I think you'd be a great person to kind of almost sum it up. Thanks.
Yeah. Okay. So for me, a campaign is the sort of the whole suite of activities that begin with planning, where you're going to burn, when you're going to burn, who you're going to burn with, who you're going to burn with, and it's got a starting point, a midpoint, and an end point. So, you know, and it's always objective driven. So, you know, in my experience, a campaign starts with, you know, okay, we have this need, this question that we need to have answered. For example, just something like, how does fire affect, or how does fire maintain biological diversity, something like that. So then we have to find a place to do it. We have to figure out how we're going to measure the right variables. Then it moves to the phase where you're actually starting to think about executing. So you have to make contact with the area that's doing the burn. You have to integrate your activities with their activities, and then you execute. And then the deliverables are often, once again, defined by the objectives. So for example, with the 2025 or 2024 Fort Stewart campaigns, one of our objectives, it wasn't the main objective, but one of the objectives was to provide a data set to evaluate quickfire and WFDS or whatever. So we had to plan in advance what kind of data we were going to have, how many, you know, design the experiment so we had a robust data set to actually be able to, you know, evaluate a fire behavior model. I'm kind of rambling here, but to me, a campaign, it's a discrete event. It's objective driven. It can be 2 investigators or it can be 100 investigators, but it doesn't have to be a giant campaign with satellites and aircraft. You know, Dan Jimenez, Louise Loudermill, and I have done these little campaigns. You know, I shouldn't call them little campaigns, important campaigns that only involve maybe a handful of investigators and a single or 2 prescribed fires. So the size isn't necessarily, in my mind, how I define a campaign. It's just this planned, objective driven event. And deliverables, yeah, I mean, there's hard deliverable. You put it perfectly. Hard deliverable is, I'm going to have radiometry in 60 points throughout different vegetation types coupled with three-dimensional fuels that I'm going to make available to whoever wants to use them. And that data set is going to be curated, it's going to be documented well, and it's going to have QA and QC. There's a hard deliverable. A soft deliverable is when you're riding around the fire and you're observing phenomena that you would never have been able to see unless you were standing next to the fire, and you have a conversation with the person, you know, and say, look at that. You know, we've all had these conversations. Aaron Pena and I had those conversations last spring. Rod Lynn and I had those conversations 20 years ago. So those are the soft, and you and I, Morgan, we had those, you know, that I couldn't find the picture of you from that campaign back in 2002, but you know, we talked about what we were observing, and then that, you know, that's the soft deliverable, which is innovation and new ideas. So the more people are involved, often that's good, but then also you can have conflicts too. You can have bad blood, and you can say, you know, my research approach and their research approach is not compatible, and that's an important deliverable as well, I suppose, but it's not a positive one. But anyway, I think that I've said enough.
Okay, I see Rod has a card up, so let's start with Rod next.
So, Joe, I appreciate you bringing up some of those soft deliverables, including the ones you just mentioned. Could you talk a little bit more about your impression about the impact on the site? I'll call it the host practitioners or the host agency, and their, you know, what's the impact on them in a positive way or negative way? But I think that's an additional thing, and maybe their impact on their receptiveness to science going forward.
Well, that's what we've spent 15 years doing. So my entire career, when I was first hired by Dale Wade in 2002, he said, the first thing you need to do is start burning with the Coney National Forest. So, you know, that's what I did. And when you know, this is a opportunity not everybody can have, but a Forest Service scientist has this opportunity where you're embedded with operations. So you learn their language, you learn what their problems are, you learn, you know, you can add value in making observations from a different perspective. So what we learned from that was like, well, we can do this if we integrate the operations folks from the get-go. So impacts on host unit have been, I don't know if we've never not been invited back. Early on, we had some issues with freelancing and people wanting to get good pictures of the fire and running out into the unit in shorts and things like that. But Kevin can talk about that. But we nip that in the bud, and we just say, hey man, this is this is an event. We are guests here, but we have a lot of value to add, and we never want to be sort of tail between the legs. We have usefulness to the fire operations folks. We just sort of need to prove it to them. And one of the ways to prove it to them is being receptive to what their world is. And for example, Fort Stewart, you know, we were having this is another soft deliverable. You're talking to an engine captain, and he's asking you questions about what is that weird instrument that you have out there? Why is it useful? You know, like, what is it doing? How's it going to help? And you can have those one-on-one conversations, which really builds a lot of camaraderie. And then they'll make an observation. You're like, that's a really good idea. We should do that. Or this is what we do normally. And anyway, so in general, the whole reason why we built the IRMT was to prevent sort of a heavy burden on the host operations crew, and also give them a space where they can feel like their input is valuable, and we build a better product on the whole when we do that. And some of the most important ideas that I've been pursuing for the last 5 or 6 years have come from conversations with fire and aviation management folks. You know, really, really interesting observations that have a lot of scientific and an example is just like, what is, are prescribed fire objectives achievable? So for example, one of a typical prescribed fire objective in the mountains of South Georgia might be to reduce overstory density by 20% using a prescribed fire. Well, then when you look at the actual energy available in the fuels, and the amount of energy it would be required to overcome the protective biology of a mature tree, it's impossible. So the conversation was, well, your science could help us build achievable prescription objectives. You'll never get there with 2 tons per acre of hardwood litter when you're trying to kill a mature tree. So those kinds of conversations show that we're valuable and our science is valuable to their objectives. And they often give us ideas that we never would have had on our own because we're not fire managers. So it's, we don't have to talk about how valuable co-production is, but by sort of living in their world briefly during a campaign, by adopting the incident command system through like the IRMT approach, we make that happen.
Marcella?
For the presentation, it's very nice. I have a question after the prescribed burn is done, you present your data. Do you have any way to track the usability of the data, track end users? Oh,
So the question is sort of like, how do we make the data available, or how easily available is it, or?
Can you track its use?
Track the use of the data. Or
I
track
didn't
the-
catch that last part.
Are you able to track the use of the data that's developed?
Track the data.
Can
Yeah,
be used?
well, yeah, so and Kevin or somebody else who's, also involved with the WFC data portal is how we do it. And I'm sorry, I'm still a little bit confused, but the way, like, by making those databases available through like a website like the WFC portal, it has a DOI and it actually tracks who's using it. And you can set your sort of publication parameters, whether it's freely accessible, open access, which is what we usually do, or can be some embargoes and things like that. But it's kind of a relatively new concept, so it's hard to track how far it trickles through the literature, for example, if that's sort of what you're trying to get at. I'm sure, if people publish the DOI of the data set, we can track that, but we haven't actually tried to do that. Did I answer your question?
Kelly?
Hi, thanks for the presentation. Really interesting and intrigued by the integrated research management team and that concept. That makes a lot of sense to me. I'm curious if you've used the same structure in other parts of the US. And, I'm aware that much more prescribed burning happens in the Southeast. So of course, that's where it's been concentrated. But I guess just wondering if you've tried to use it in other parts of the US and what might limit that or not.
I personally haven't, but I know that the IRMT team has worked out in I believe it's Sycan Marsh out on the West Coast. And yes, it's implicitly designed to be non-geographically sort of limited. The principles that it's based on are the principles that guide all federal and a lot of state wildland fire management. So it's something that would speak to somebody in California as well as it would speak to somebody in Georgia. So that was always our intent, was this was not going to be a local phenomena. And I will also tell you that I've used that when you start out as a firefighter and they make you take like I-100, which is the introduction to the incident command system. They use an example of, you can use this to organize a party. So you have a branch commander in charge of beverages, and so you can use this as a way of, whenever you have any kind of complicated multiplayer event, you can use this system, and it's been proven, and there's papers written on it, and it's used in the military, and it's used in emergency response, and it's used in fire. But I used it in science when we had to organize, there were, I don't know, 75 people doing research on the 2016 wildfires in the Southeast from the Southern Research Station. And the station director was needed to brief Washington, and he said, he called me and he said, I need to know what everybody is doing on these 2016 wildfires. I'm like, well, there's 60 scientists. So we immediately just leaned on ICS. We created watershed impacts, economic impacts, wildlife impacts, fuels impacts, all kinds of different bins. And then you could identify leads for each one of those, and they could gather the information much more efficiently. So there's this concept of span of control that you can leverage so that you're more efficient. So instead of me trying to call 90 people, I can talk to 3 people, and then they talk to 3 and they talk to 3. So anyway, yeah, the system has been revolutionary in how I sort of approach my own research campaigns, and it's widely applicable, and it's applicable anywhere in the world, actually. So, and I'm not overstating.
Okay, so we have 3 now. There's Albert, the Ilke, and then Kevin. So let's start with Albert.
Yes, thank you. Hi, Joe.
Hi.
So I have a couple of questions for you, and I realize that it may have evolved in time, but examples would be very useful, I think. So the first one is what kind of scientific issues or challenges you got in implementing the campaigns, and I'm taking examples like incompatible instrumentation, things that were influencing each other, the difficulty to get some data, these kind of things. And the second question is, how do you design your campaigns, in the context? So was there a design with the need of, for instance, lab experiments, the field experiments were used as setting the range for the lab experiments, or was it used to provide data for modeling, or all of the above? But examples would be
Sure. Yeah. So one is just the lack of instrumentation that you can put into a fire to collect the kind of data that you need. So innovation in terms of building sensors that are going to collect high resolution spatial fire intensity measurements that can also be deployed interior in a burn has been a challenge. But it's been a big part of the innovations that have occurred because, you learn how to protect something or burn something, you learn its limitations. And then, Bob Cremens and others, Matt Dickinson, have been doing this for years. We've been working together and we are at the point now where we do have inexpensive, sort of intensively deployable systems for capturing fire energy, radiant energy release. The next sort of holy grail would be convective heat, capturing turbulent convective dynamics in a intensive enough way to understand the huge amount of energy that's being transferred through convective heat. My segue for that is conflicts between, and this is not personal conflicts, this is instrumentation conflicts. In the Eglin Air Force Base campaign in 2023, we had a group that was really interested in acoustics. They were deploying all these pretty sophisticated acoustical sensors to try and track fire energy release through acoustics. Problem was, it was a noisy environment. There was a helicopter ignition. The sound frequencies being emitted by the helicopter were swamping some of their measurements. ATVs and engines running around were creating a lot of noise. And so we ended up, I'm working with that crew right now to design a quiet campaign. So they were able to get good measurements, but not as good measurement as they could have if it was a quiet fire, so to speak. And they're also going back to that holy grail of convective heat mapping. They're doing some really innovative work in using acoustics to sort of map turbulence. But to do that, we're working on a campaign with them right now, locally, to try and find some areas that will be quiet and that we can actually do some field experiments that are going to be coupled with lab experiments. So yes, once you have those conversations and when you execute and you see, okay, perhaps they weren't paying attention when we said it was going to be an aerial ignition, or they didn't know what that meant. But that was a lesson learned for us. Like, okay, if you're measuring acoustics and it's an aerial ignition, there's going to be a helicopter flying around. So I don't know. I don't know if that answers your question. But yes, I mean, there's always, I'm not saying looking at a tiger in the zoo isn't informative and important, but the synergy back and forth between field and lab and field and modeling, you still got to have really solid field work to inform both of those, in my opinion. And another example would be some of the work I've been doing with Dan Jimenez on looking at fire break sort of hardness, or what is the width of a fire break to be effective. And so we did a lot, like Dan leads this, but we did a lot of lab work, and then it's transitioning to the field as well. So anyway, there's, just having those conversations and those experiences really can spawn new opportunities.
Okay.
Hi, Joe. Similar question, actually. I really appreciated that you said a campaign is an event driven by objectives, and has an end and a beginning and an end kind of thing. How do you design the objectives? What is that collaborative process? And once the campaign ends, how do you define impact after it in terms of reuse and what kind of things it leads to as a part of, especially what the mission agencies that funded it, but also other things that are using it in terms of science or other practical aspects. And
I think that's a really interesting question. So I'll just use one example that I feel like is working. So when we thought, okay, we have quickfire and we're trying to build quickfire as an operational prescribed fire model. One of the first sort of hurdles is believability, not only for informing the science behind how quickfire works, but those who are going to use it are going to need some proof that it actually captures realistic fire behavior. So one of the main objectives of the 2024, actually all the IRMT campaigns that were done at Eglin and Fort Stewart, was how do we collect a robust real fire behavior measurement data set. So one, we're going to need many, many, many instruments, more than we have. How do we build new instruments that we can deploy? We can put out 50, 60 of them. And those those instruments have to be able to collect relevant information that will then provide a independent data set to evaluate a fire. You could use it for a WFDS, you could use it for quickfire, whatever. So the way we had to do that was our objective. So one, we had to look at the instrumentation angle. We had to look at the statistics. We consulted with statisticians, like, what is the sort of robustness, the power of different sampling approaches. And so that is what we ended up executing. In terms of impact and utility of the deliverable, some works great, some doesn't. We're right now just finishing up a publication where we looked at, does the quickfire output, capture the real fire behavior, and how can we tweak the input parameters with different levels of fidelity, and what kind of an impact does that on its performance. So that's, a peer-reviewed publication is obviously one of the gold standards for the utility of your exercises. But there's other, just instrument development. It's not as sort of glorious, but it's important. And understanding that we need to build cheap, rapidly deployable, and semi-disposable sensors because it's a fire environment was another offshoot of that that's been highly successful. So does that get to what you're looking for there?
That's very important. And I couldn't help but say, if you put an M between your O's and it's an OMG.
Right. What is it? They say, I don't know how much of R&D ends up with dead ends, but it happens, but we still even learn from the dead ends.
So I think Kevin would like to ask a question, and then we have Talat.
Joe, I think you sort of touched on a couple of points for the organization and implementation of campaigns that I think I'd like to just bring, bubble up explicitly. One is safety. The team, because a lot of research is trying to do things that aren't typically done on, in a prescribed fire environment. There is some additional exposure to hazards for staff, and the ability to really keep everybody safe is essential. And I would like to kind of hear your thoughts on that and its effectiveness in that regard. The second is sort of credibility with the IRMT. Again, you touched on these soft skills, but to be able to have research in a campaign sense, doing innovative work with managers who are responsible for implementing the fire, to bring that credibility through the IRMT seems to be something that you were really emphasizing, but it's kind of foot stomp that as an important characteristic defining success and feedback. So failure too, identifying failure, that credibility comes with the trust to say, hey, that didn't work, or if you'd have done this better, you might, or you done differently, it might have been better outcomes. So just want to get you to comment on those.
Sure. Yeah. Our safety record has been exemplary. And the whole point of leaning on the IRMT sort of model is that we have safety professionals. That's their job. You're not depending on individual researchers to have to expect necessarily completely how to be safe in a hostile environment. So, we have trainings, briefings, people who are actually, we've actually facilitated people getting fire line qualifications if they really need to be next to the fire. But we lean on people that do that for a living. So our safety officers. You can do this on a much smaller campaign the same way. We have tailgate safety sessions, we have job hazard analyses, things like that. But I think the beauty of sort of the IRMT approach is that you're leveraging a professional, so that takes a lot of burden off of the individual. Like, everybody's ultimately responsible for their own safety, but there is a lot of guidance there to keep you safe and know where to go and how to behave. And there's escorts. And so we have a whole system where the primary goal is safety, right? I mean, that the IRMT, one of the primary objective besides meeting the science objectives is keeping everybody safe. That's obviously always the number one concern. But by using this system, you're building in professionalism at that level, which helps the researchers make the right decisions, and they can point out problems, and then you can readjust and still get your work done. In terms of credibility, once again, if we come in with a safety plan, if we come in with sort of all the logistics, communications, all these things, and we're using ICS forms, we have a 205 for communications. We're managing who's going to talk to the operations person, and how do we have an efficient flow of information back and forth across those two worlds. Once again, we lean on professionals who do this for a living. You can do this at a local scale as well. You come up with a communication plan, you come up with a safety plan, you come up with an operations integration plan, things like that. We've written a whole guide on how to do this. It's almost ready for publication. That will be freely available, and you can take parts of it and use them or not. But it's building on professionalism that is exactly the same world that the fire ops people work in. So that inherently builds credibility. When you show up and you throw down, your staffing chart, and you have an org chart showing who's going to be where and doing what, that immediately builds comfort and credibility. Does that answer your question? Okay.
A lot.
Hi, Joe.
Hey.
When I saw the word conflict on your slide, a different example came to my mind. You gave a very different example. Excuse me. I believe this was Fort Stewart 2024. On one of the burns, the smoke team was asking for a later ignition for the winds to settle in a certain direction that they planned for. And the fuels team was asking, for an on-time ignition. Can't remember the reason why now. Maybe you do, but perhaps the fuels were getting too dry. And also, the site managers, of course, they have their own objectives. So when there are objective conflicts like that, I mean, the researchers are embedded, to the operations, the operational objectives conflict with the research objectives maybe, and then the different research teams' objectives conflict with each other. How can we plan better to manage dynamic situations like that when, you have to make a decision in a very short time? How can
Right.
we plan in advance
Yeah.
for?
Yeah, that's the $1 million question there. When you have a large campaign like that, where you've got, I don't know, we had 60 or 70 scientists, each with their own objectives and each with their own instrumentation, there's going to have to be compromise. And in general, what I would say in most of these situations, we lean on the operations folks to give us the guardrails on ignition time, for example, or ignition technique. So we have to, as researchers, understand, okay, this isn't all about me. I have to compromise. Sometimes we have to go back to back, and I would like to have 2 days between to rehab my equipment, but I have to go back to back, so I'll do it. And that means a lot of maybe a compromise on my part, because I'm going to lose data because some sensors didn't have time to be rehabbed. But yeah, no, that's something, that's where the planning phase of the campaign comes in, where, if you know that you need those specific sort of parameters to get good data, generally the IRMT will bend over backwards to try and figure out a way to make everybody happy. But, yeah, I mean, the spirit of friendly compromise and flexibility, and also being upfront with exactly what your needs are well in advance. So a lot of times in some of these campaigns, we deal with them, but we're throwing curveballs at the last minute saying, oh, I need this. Well, I wish we would have known that a month ago or whatever, but we still try to deal with it. And yes, it's not perfect, but I think the value added of having all this other ancillary information that's going to inform your science, even if you don't get the perfect measurement for your specific question, the good outweighs the bad, I would argue. That's at least my perspective, and I'm, biased, I suppose. But yeah, compromise and clear, advanced details on specific needs, and then we can start figuring out how to balance those with everybody else. So that's, early is better, and remembering that you're going to have to compromise. I don't know. Nobody likes to compromise, right?
Do we have any other questions? Is Stacy, you guys seem to be raising your thing.
Yeah, just want to, that everybody around the room has an opportunity to ask any remaining questions. We do have one question from the audience on the line, and I'm happy to take that now, but I want to make sure we give priority first to committee members if there's any remaining questions for Joe. Okay, with that, I will ask Louise Loudermilk, if you'd like to ask your question now. We do have a little bit of time, so if you'd like to take yourself off mute, you're welcome to do so.
Hi, thanks everybody. So Joe, I wanted to ask you if you could talk a little bit more about co-production within and outside the campaigns, right? Because co-production happens kind of, all the time. And this could be like within the Innovation Landscape Network or beyond. So, yeah.
Yeah. So, I've been sort of focusing on the event, the actual burn, but Louise is right. When we start planning, we're integrating with the operations people months in advance. We need to get access to the site. For instance, Louise's team needs to go down well in advance of the burn, and some of these areas are restricted if they're on a military base. So there's a lot of logistics that go into that, but every time they go down there and they're speaking with the staff at Fort Stewart, for example, there's this co-production happening in an organic way. They're saying, "What are you doing? Like, what's going on? Why are you doing that?" And then sometimes people volunteer to help. They'll go out with Louise's team and either guide them through the complex, logistics of getting from one site to another on an active military base. And there's conversations that have in the truck. So the co-production starts with the planning. It obviously reaches sort of an apex with the event, but then we've all been going down to Fort Stewart to share our results to the operations folks and give them an opportunity to chime in and understand how important not only their work was in making this happen, but add some value and also see what this sort of what the utility of all the effort that they put into hosting us is, how that's realizing. So that's something we all have to do as researchers is take the extra effort to reach out to the operations folks and explain what we're doing in a way that's going to be useful and open up your ears to hearing different points of view from them. So yes, it's a continual process, and we also do this, in order to sort of build our capacity to be able to do this. We go out regularly and just burn operationally. We're not doing research. We're just helping them do prescribed fires. And if you have an opportunity to do that kind of work, that's been crucial to our whole fire lab sort of success and our sort of skills, is that take every opportunity you can just to go observe a fire, even if you're not working on the fire. And it doesn't have to be a NWCG fire. It can be somebody's private property if you live in the Southeast or, anywhere. But then you have these one-on-one conversations with the people doing the work, and yeah, co-production.
Well,
I don't
I
know,
was
is that-
also, I was also thinking, Joe, just about like, feedback on, like on the models and,
Sure.
sort of improvement on the data and the models and things like that. So.
Right. And that is the heart of the EILN, right? Like, so the users are providing feedback onto utility and what's missing. I think Louise, you used an example where like with TLS metrics, you can come up with 1,000 different metrics. But then we had a conversation. We're like, well, we need to have like some metric that tells us how much hazardous fuels were reduced, simply one number. So Louise was like, aha, okay, this is something we can do. We can put our heads together to come up with a really kind of compelling story on how TLS can inform, fuel management and quantify it so that you can actually have some kind of metric of your success. So not having that conversation, you might focus on some more abstract topologies of fuel, structure versus, what was the percent of, heavy fuels reduction, something like that. So yes, it's important for us to get exposed to the users and the people doing the work on the ground in order for us to give better science to guide whether or not that work is going to be more efficient and more successful, that kind of thing. So you should probably just say what you need to say.
No, it's all you, Joe. It's all you.
No.
Do we have more questions? Speaker is going to be coming on in about 5 minutes. And so I think we could briefly run and grab coffee and do the things we need to survive.
Thank you so much.
I hope you're able to survive my talk.
Oh, it was great. Thank you.
Should I stick around or am I relieved?
You're welcome to stick around, but your official duties are completed.
I'll stick around as long as I can. Thank you. Thanks for the opportunity, by the way.
Likewise. Thank you for joining. We'll take a 5-minute break and convene promptly at 11:15. because we are on a quick break. We should be reconvening momentarily, getting started again promptly for the next presentation. Joshua, thank you for your patience. I think we're just about to have everybody back in the room, so we'll go ahead and get started here momentarily.
No rush.
Thank you all. I think we're going to continue with our next presentation. So Joshua, I'll turn it over to you and ask that you introduce yourself and go ahead and get started.
Hello, everybody. Thanks very much. My name is Joshua Schwartz. I'm a research scientist focused on aerosol. And I'll be sharing with you information about this FireX AQ intensive campaign. Can you see that presentation?
We can. Thank you so much.
Great. So, you know, this figure is meant to highlight the main theme of what I'm going to be talking about, which is that we wanted to solve every problem there was, and we wanted to include every community that we could. So because of the scope of this, I'm not going to have time to say everything I should. And so right at the beginning, I just want to say, you know, this was initiated by NOAA. It was really heavily driven by NOAA and NASA, but it was fundamental to have contributions from the National Forest Service, industry, academia, local, state, and other federal agencies. So really a big effort. You can see the platforms, and the point is, from the beginning to the end, we were interested in contributing to those questions, but the perspective I'll be sharing is really from the research side. So the way I've organized this presentation is kind of following the charge that I saw for you guys. So first, just the facts, the overview of the activities, then lessons learned, and I'll be focusing on just, you know, picking out a few publications. It's really the publication record that is, as far as we're concerned, represents what came out of that campaign. Publications are still coming out, so that isn't over. And then finally, the future needs. And what I did was I reached out to some of the people that I felt had a really big impact, not all of them, on FireX AQ, and asked for their input, their impressions of what's needed in the future. And I don't have time to go into everything, but hopefully you'll have it as a reference from this presentation, and I'll highlight a couple things that I think are valuable. All right, so FireX AQ, one of the big schemes was to try and incorporate observing schemes across the whole length and temporal scale in order to provide really robust science, and science that was going to be useful for whatever scale of modeling, et cetera, we were interested in. You know, I'm not sure what your scale is. I don't think we did a great job on very, very small scale fire processes and spread, but if you're interested in air quality and larger scale impacts, then I think we're well positioned. So what this slide shows is like a bunch of specific topics that we were interested in contributing to, and in red, I've just circled the ones that I kind of think were a little bit higher on our priority list. That's the outside. Then the green box on the inside kind of represents the more generalized needs. NASA was involved. There's a strong emphasis on validation of satellites and making sure that satellites are really very useful. For example, of course, we wanted to help modelers improve fire emissions and so on. And then you can see these platforms from satellites, aircraft, something on the ground. Right now, I just want to point out that I'm not really going to be saying much about the models, because they weren't part of this observation intensive in quite the same way. But there was a strong buy-in that we had encouraged early on. There were 16 models that provided daily forecasts that helped us decide where we were going to put our assets on any given day. And I think, you know, there was a lot of support for model development and improvement and validation. All right, so just the facts about FireX AQ. Here you can see a graphic showing the chain of measurements from the satellites all the way down to the ground. So up top, we had a lot of support from the satellite community. We had people from those communities interfacing with us. So every time we were planning a flight, we had information about 6 different satellite overpass times, and we're able to try and coordinate sampling to match those. Of course, there's geostationary as well. Below that, we had the NASA ER2. It's a high altitude research aircraft, kind of like a steerable satellite, so a lot lower, a lot higher resolution, mostly carrying satellite emulator instrumentation and drawing this chain down lower. Below that, the NASA DC-8, this was the premier research aircraft. It held like 35 scientists, the way it was configured for FireX AQ, and it had in situ and remote sensing payloads. It was focused on sampling smoke at various ages and exploring evolution. Below that, two smaller aircraft, NOAA Twin Otters, with two different objectives. One was focused on chemistry with a much smaller payload. It was something like a couple scientists that would fly on these planes. And that Kim Otter was able to kind of probe more into nighttime chemistry. We had one with remote sensing 3D wind LiDAR. We called the Met Twin Otter, and it was interested in exploring the fire-weather interactions that I think probably are on everybody's radar. Below that, fixed and mobile ground sites. So we had two mobile vans that were very well instrumented, one from NASA, focused largely on aerosol, and one from Aerodyne, an industrial partner with a lot of chemical aerosol information, but very broad. We also had Aeronet Dragon. So this is a deployable mobile, essentially Aeronet sites, sun photometers, and it could be placed, for example, a bunch of them at different altitudes and valleys in order to get differential information about the impact of smoke on light field, right? So relevant to climate, satellite assessments, all the rest. On the ground, there were long-term observatories that give a much wider perspective about smoke, and we wanted to make sure that we were able to contribute to those kinds of more climatological questions. There was some effort to make those, at least some of them, kind of more robust just during the sampling period. And finally, it was really important to us to have a really strong connection to fuels so that we understood where the smoke was coming from. So there was a lot of buy-in from the fuels community, and the smoke we sampled was really almost entirely from fires where at some level the fuels were characterized. Here's the geographic temporal scope of the intensive component. What you're seeing is flight paths for those four aircraft that I mentioned. A lot of flights in the Western US from those different platforms. That's also where these mobile labs were deployed. That occurred for about 3 weeks from the end of July in 2019. Then what happened was most of the aircraft went away, but the DC-8 transitioned to flying out of Kansas. That's these red tracks that are over the central and southeast US. And it focused at that point on sampling on its own agricultural fires and prescribed fires. So that was another couple of weeks. The ground sites, there was at least 4. And as I mentioned, the perspective is of much longer term measurements. But we were really interested in making sure that those gained some value from the detailed in situ measurements, and also there were the possibility for connections from our measurements in really very young smoke to eventually, let's say, fully evolved smoke at those sites. And I think there was some point I wanted to make about that. Let's see. Right. So, you know, this graph shows just a few sites, but we did have buy-in from state agencies like CARB. And so I know that there was also more ground-based sampling from the wider community that was aware of these activities and knew that there was the opportunity to kind of build off of a very intense data set. All right, the data outputs, I've split these up into first showing you something about in situ measurements from the aircraft and from the ground. You know, the DC-8 is incredible in its capability to have really a huge laboratory of different instrumentation, and it covered a tremendous amount of species. The kind of generally divided measurements we were focusing on was things like tracer measurements, reactive nitrogen, VOCs, their evolution, hydrocarbons, oxidation products, chemistry, and all into gas phase, and then aerosol phase, and those interactions between aerosol and gas phase were really important as well. So on the aerosol side, we were characterizing the composition chemically, the physical size distributions, optical properties, also extending into the coarse mode and cloud interactions. This blob of something you probably can't really make out is just a list of the data products from the DC-8, more than 600 data products. So like each element might be something like propane concentration, aerosol size distribution, you know, furfuranol, etc., ozone. And then we also had remote sensing outputs, and some of those on the DC-8. The ER2 was entirely remote sensing, and as I discussed, one of those twin otters. So active LiDAR, this was really useful on the DC-8 because we used it to decide where the plane would fly to best sample smoke, but it also gives a much wider perspective about the size of plumes, the extent, and a lot of insight for comparison to transport models. Passive radiometers for these in situ payloads were really useful for actinic flux, for photolysis rates, and the like, the way they change within plumes. And then scanning spectrometers. The figure that I'm showing you here is an IR picture on the right from the MASTER, the MODIS MASTER image, satellite emulator. It was actually on the DC-8. That's the Williams-Flats fire, which kind of was one of the primary fires we sampled a lot. That was very exciting. On the left is just the visual image. All right, so what are the lessons learned from FireX? As I mentioned, we, in the research side, really see it as the papers that came out. There was more than 85 papers published, more on their way. And what I've done is I just walked through all of those papers and kind of organized them by broad topic. And what I'll do is I'll just point out a couple of things. One was, I think that when you look at the outputs, there was really a very strong emphasis on emissions characterization, emissions inventories, emission factors, and so on, and for different species, for aerosol, for various gas phase species. That was really very productive area of science for FireXIQ. And of course, those things are relevant to kind of larger scale air quality questions. Fire radiative power was something that was very much on our radar from the beginning. And all of the platforms from satellite ER2, DC-8, and Twin Otter, all of those had some ability to measure FRP so that we could cover that whole length scale of resolution that was interesting, and temporal resolution as well. And making connections to the emissions was a high priority. So there's a lot of focus on that. Of course, connections to plume rise models, validations of those models, assessing the impacts of those models, of the plume rise model on model transport and so on. All of those things were explored. And I would not at all say that those problems are solved, merely that we contributed to understanding the scale of them and the impacts of various schemes of evaluation. Let's see, some more papers. And here I wanted to make the point that there's some instrumentation papers. That was also, I think, a well-represented component of the literature coming out of FireXIQ. And this can represent things like brand new instruments. So in fact, the FRP measurement that we had in the Twin Otter was a brand new measurement developed in this laboratory to support that need, but also validation of instrumentation and comparisons of different techniques to achieve the same information. So you have a LiDAR, it's really great for measuring things remotely, but you like to compare against in situ, and maybe you discover some question about validation, but also maybe you discover some synergy or more use or a parameterization that then extends the value of the LiDAR, the satellite, what have you. And I think that's a really important component of FireX, where it was very productive. You know I don't have so much time to go through all of these papers. One that I do want to point out is that there was this study on the influence of wildfire smoke on indoor air quality. So we were very excited about making sure that the measurements we made would ultimately connect to societal needs like air quality. And so here's an example. I hadn't really understood that, that the indoor air quality would be so strongly affected. Apparently, the study showed that, yeah, people close their windows a lot more. There's a lot less exchange of air from outside, but because of the enhanced wildfire smoke, there's still important impacts. So, so that was interesting. Okay, I wanted to share just a little bit of my impression, you know, kind of making a guess at what your interests are and needs are in terms of the scale of the modeling. And I just want to make a couple points about some takeaways from FireXIQ before sharing a little bit about my broader community's sense of the need for the future. So one is the statistics. And so we were able to sample some prescribed fires in FireXIQ. You know, I remember the name Tall Timbers. I remember FASME. So we did have that opportunity. And I think it was really wonderful to have a chance to have like an ultra well characterized fuel and burning conditions and all the rest. And that's terrific for us on the research side for pursuing our interests in understanding mechanisms more fully. But in terms of the larger air quality questions and those scale of models, I think that it's the statistics that really are much more important for us to continue to make progress on. So I'm working on an analysis, for example, of aerosol size and fuel relationships, and you know, having one fire really well instrumented isn't as valuable for that particular question as having a whole bunch of fires of different classes that can be combined in order to make our best guesses. I think that also probably goes for plume rise, right? It's just for the large scale models, I don't think we're at the point where the ultrafine detail is the limiting factor yet. Data collection. This was something that was really interesting to see occur in FireXIQ because we had such a wide range of assets. So I'll give you some example. The Twin Otter that was looking at chemistry had a tiny payload relative to the DC-8, but it flew very slowly. It needed to be refueled, so it would refuel and come back to the fire. And the result was that it was really well suited for doing Lagrangian style sampling of the smoke plume, for really getting at this aging processes in a Lagrangian sense. And it turned out that analyses of Lagrangian sampling of smoke were a lot easier from that Twin Otter than they were from the DC-8. On the other hand, the DC-8 had that huge payload, so anything we wanted to know about, there's a chance we were able to measure it, and we were able to cover whole plumes. So I remember smoke plumes extending, 150 kilometers, and we were able to characterize all of that smoke plume at different distances from the fire. So it really depends on what you're interested in, how you decide to instrument things. Then, the DC-8 is absolutely fantastic in that it holds more than anything else, but it just can't fly on the ground. And it was really the mobile labs that were able to sample extremely fresh smoke, initial condition smoke. There was no chance for us to do that with the DC-8. We could get smoke that maybe was 10 minutes old at the earliest from the larger fires. And then finally, flexibility. So, going into FireX, I was under the impression that prescribed fires were like, oh, you push the button, done, set it up for what's going to be convenient for us. Having left FireX, it's clear that the people who are running the prescribed fires have their own constraints. And so there was a fire called the Blackwater River State Park prescribed fire in Florida. And there was a plan to light it at a certain time. We were getting the aircraft ready to fly to meet it at that point, but circumstances contrived to make that fire start early. And so we tried to adjust, but I think that in the future, knowing the steps it takes to get a plane like the DC-8 or even a Twin Otter into the air, the preparation, we could have done that a lot earlier and then kind of stood by on the ground in a readiness state, and we would want to do that in the future. For analysis, there was a couple that I wanted to point out that were published, so I could have mentioned it then. One was that there was a really interesting analysis of smoke plume chemistry. And one of the issues is you're flying through these plumes. It's a real plume. It's not a Gaussian plume like a model might represent at some level. And it was really hard to deal with the heterogeneity. And it turned out that there was a really nice normalization that could be done that made that analysis a lot more straightforward for chemical processing. And the other thing I want to point out was we had Chris Holmes from Florida, who is focused on transport questions. And he did analysis using different reanalysis wind data products in order to explore variability in smoke age at different physical distances from fire and so on. And I think that that's an analysis that was very powerful for the transport questions and couples to probably the fire weather issues at low altitude. Okay, well, so this group that I reached out to, I got quite a strong response from them. And I just want to describe a little bit about these people's perspective. So Bob Yokelson, probably everybody knows Bob, a very well-established smoke scientist, fire scientist who understands, I think, all the aspects operationally as well as research level. He had a lot of comments that focused largely on fuel conditions, fuel moisture interactions. Steve Brown is a chemist here in Chemical Sciences Laboratory of NOAA, and was pointing out still some needs for chemistry, ozone production. Dave Peterson is a meteorologist. He was one of the primary weather forecasters in FireX IQ. He was able to predict with his team a Pyro-CB event during FireX that we were able to sample. And so there's some needs on metrology. Amber Soya is one of our lead contact on the fuels community side. And so, I think she and Bob had some similar types of needs they identified. Jack Dibb is an incredibly accomplished aircraft research scientist and made some points about these kind of larger questions about what are you trying to get out of the models and what's really valuable to you. Brad Pierce is a satellite and modeling expert and had some interesting points. Actually, I'll jump forward to that about kind of larger scale needs might be beyond the scope of this committee. I'm not sure about, continued high temporal and spatial resolution FRP for mission inventories and so on. And, made some points about you've got the geostationary satellite with lower resolution, great temporal response. You've got the orbiting satellite with better resolution, but no temporal understanding most of the time. And can you do something with like a fleet of very low Earth orbit detectors or something like that to get both those things together all the time? Mike Robinson is another chemist in the group here who felt that we really, if we're doing it all again, we would want to try and do better on the interactions of wildfire smoke, prescribed fire smoke, agricultural fire smoke, and urban pollution. That the HVOC interactions that we still need to do more on that front. And then Ravan Ahmadov is a scientist here who supports the NOAA high resolution rapid refresh model. And he made an excellent point about ground networks for measuring surface radiation and how it's so limited now. It's really a constraint on kind of a long-term validation of the transport models. And so with that, I believe that's the presentation I've got for you. I just want to acknowledge again, it really is a very, very wide community. And I'm sure I didn't mention some folks, but you see some names here. And thanks for your kind attention. There are some additional slides that I'm not going to show, just with a little bit more detail about the airborne platforms. So with that.
Okay. I think we have some questions to ask from the committee. We start off with, probably no surprise, Rod.
Emission factors and plume rise, and to me that says that you somehow got a way of at least approximating or including the heat release rate and or consumption rate. And I was wondering if that was just estimated by end results And if so, how are those measured on this wide range of different kinds of fires? But if it was measured, how are you getting at those numbers? Because I think that's an important integrating, when we think about integrating across scale.
Yep. Yeah. Good point. And of course, very much a focus of attention. So I just lost my train of thought. Right. So the point I'd make is there's many different pieces of information that we were achieving, that we were collecting, that were kind of relevant to this question. So the FRP part was one side of it. And of course, there's been comparisons about FRP. And then the mission side, which we could measure with remote sensing. We were flying with a LiDAR, and we had the CPL on the ER2. So we were able to characterize the physical extent, right, of smoke plumes very well. And we knew the winds, et cetera. So there you have a flux, there you have a very direct measurement of emissions. And then to connect it to fuels, the fuels community was doing some kind of approximations based on satellite retrieval of burned area. And occasionally, I believe there was physical inspection of the burned area. There was fuel LiDAR flights on certain flights. That wasn't for everything. It was just where there happened to be an opportunity. And then applying either a diurnal cycle that was just assumed or based on the FRP, they would kind of break up that burned area with their information about satellite fuels, et cetera, in order to make an additional estimate of essentially fuel loading and total carbon being released from the fire at the point that would then make the smoke that we were sampling in the DC-8. So these were really primarily available for the Western wildfires, the larger fires. We don't have that kind of information in the same way for the very small agricultural fires. Those were producing plumes that were, might last just 1 or 2 seconds as we flew through them in the DC-8. But there was characterization of the fuel type, the particular crop that had been there that was being burned and so on. So there's a number of different ways to get at those questions. And I think there's a number of techniques that are in the published literature now from FireX addressing those questions. I'm not an expert.
So let me just tag on to the question of one more thing, and that is, did you have any way, or was there any effort to differentiate especially on the wildfires, the cranking head fire as opposed to the flanking portions of the fire or backing portions of the fire, or were you at the position you were looking at was just all conglomerated? Here's what we see.
Yeah, that's an excellent question, and the answer is it depends on the platform. So for the DC-8, for example, we couldn't fly that low. We did occasionally see, I mentioned heterogeneity in the fire, in the smoke plumes from the Twin Otter. We also saw that in the DC-8. So for example, in the Williams Flat fire, there was one occasion where there was 2 portions of the fire, perhaps with different characteristics. And the plumes from those fires were separated in such a way that we were able to differentiate them in earlier transects close to the fire. And as we extended downwind, it all kind of combined together. So for the DC-8, for the most part, we weren't, what we're looking at is the really intense smoke. We were aiming for the most concentrated altitudes. And so I don't think we have the kind of very small length scale information that perhaps you're referencing here. From the Twin Otter, the winds measurements were, of course, done all over the fire and less sensitive to these types of need for intense smoke. So perhaps there's some information there at the smaller scales, at the different portions of the fire. My sense from my community, right, is that we haven't done a fantastic job of making progress on the very small scales and the interactions with the communities that are interested in fire spread and that kind of thing. So limited resolution on fuels information and burning rates connecting to the actual smoke we measured. One point also is I mentioned that the mobile labs were able to get very close to fires. So there, there's pictures of flames right next to the van. And so there, I think there is a chance to kind of understand the emissions right at those very small scales.
Thank you.
Morgan?
Thanks for your presentation. You touched on a few topics that we have been wrestling with. And I just wonder if you could talk about them directly. And that is, we were wrestling with the idea of what is a campaign, what's not a campaign, you know, a series of disparate measures or somewhat coordinated research activities versus what a campaign, you know, whatever that means. So interested in your take on that. And then you started to, interestingly, in your presentation, you really were getting at sort of lessons learned or, you know, the next steps. That was really helpful. You learned a lot of stuff, but it tends to spawn more questions. And I wonder if you could kind of speak to that too, as sort of, those are both sort of, you know, beyond the number of papers, beyond the number of scientists involved. So if you could just speak to that briefly, it'd be helpful.
Sure. So first of all, campaign and not campaign. So the community that I come from does airborne campaigns. And so what that means is, you know, it's a dinner with 3 courses. And the first course is a lot of preparation, setting up instrumentation, deciding logistics, trying to involve collaborators that would benefit and that could benefit our scientific goals. That's, I guess, the appetizer. And then the main course is, wow, you have everything on the plane, you go out there and you fly. That's what I would call the campaign. And then afterwards is actually the most important part. Dessert is where we get the analyses done and the papers start coming out, right? It doesn't matter very much if somebody like me learns something and doesn't share it unless I'm going to be involved in planning the next mission, right? But it's really having a careful look at the data, understanding it, and you know, letting that develop into learning. So the campaign for me is really just an intense measurement component. Those ground sites that we were collaborating with, to the extent that they expanded their observations or focused them on this time periods with additional information from the aircraft and the assets that we had, I would say, oh yeah, that's part of that campaign. But I don't consider a whole large scientific topic like prescribed fire smoke modeling to be like a lifelong campaign. So for prescribed fire, if there's one fire with a bunch of collaborators, really carefully instrumented and so on, that probably would be a campaign in my way of thinking. For the lessons learned and next steps beyond the publications, you know, I don't really know the full charge for this committee and what your interests are, right? And so that's why I made the point that if it's in air quality and air quality impacts, for example, from fires across the U.S., wildfires as well as agricultural fires, but broad scale impacts, then I don't think we really need to worry too much about, let's call it, the extremely fine details of the smoke processes, the chemistry, the composition. I think that we know that better than we can make a connection to air quality. And it's really to transport the plume injection height, the statistics. If somebody could make a, let's say, less noisy connection between a parameter like fire radiative power with known meteorology, and then, you know, have a successful output of smoke injection height and distribution, even in mountainous areas, right? Even with all the topology, wow, that would be really great because it's so important for those larger questions of air quality. So my feeling is that you really have to know that the question you're asking in order to be able to set up to answer it. And so if it's large scale air quality, I say go for statistics. You know there's going to be fires, great. You can characterize the fuels well, and you can go in afterwards and you'll know exactly how much, or you'll know better about how much is burned, et cetera. And then you can connect that to the smoke, great, and connect it to the output heights, et cetera. Does that touch on does that satisfy?
Does, I mean, I think there's sort of a, I don't know, one of the primary metrics, everyone's going to say, you know, we wrote 68 papers, we wrote 34 papers, you know, that sort of stuff. But I think we're keen on the emergent, beyond the, you know, the 84 data points. What is this?
Yeah.
How does something like this chart the next chapter? How does it chart the next? What does it mean for the next campaign?
Yeah.
That's a harder thing to pull together. But I mean, I think you've done a nice job by relying on some key scientists involved and sort of what they see as the next steps. But that part seems like that's a big value beyond just here's what your money gave us. You know.
Yeah.
Here's what it. But thanks. That was good.
Sure. So, you know, I can't remember if I made the point that those needs, you know, it's, I think, 3 pages of needs from these scientists, really reflects their scientific interests. And it's not clear to me that that reflects the needs that this committee is going to identify for the kind of perhaps much narrower focus that you want to advance. But I really think that one of the main takeaways from FIRE-XAQ is you can't do everything, right? And what you can do, you better make sure that that satisfies what your ultimate goals are.
Kelly?
Thanks for your presentation. And I'll give you a chance to punt this question. You may not be the best person to answer it. We've been talking a lot about in our meetings, you know, co-production at different stages of campaigns and really integrating efforts, right? So this gets back a little bit at what you were just saying, that, you know, the needs and wants of the scientific community may not necessarily connect with other partners. And so you started actually by talking about this aspect of FIRE-XAQ, right? That there were these state and different agencies and stakeholders, but then you kind of just skipped over that and went to the research. So I'm curious to what extent you think that the multi-stakeholder aspect was successful of FIRE-XAQ, and if you could give some examples, and again, fair to.
Sure. That's a big challenge. And, you know, when we started out, it's so easy to say, oh, well, we'll include everybody and we'll have community scientists and we'll have outreach. And I think we tried to do all of those things, right? We did make contact with all of these different levels of agencies, universities, et cetera. It was very well advertised. And but the way that the science works is that we lose interest after we answer our own questions, right? And so the scheme was, oh, we'll reach out to these people. They're really interested in, let's say, health impacts. We'll say all of our data is available online and they'll use it. And so it's our engagement with those communities that quickly dies away, in my opinion. So perhaps COVID had something to do with this, right? 2020 after a 2019 campaign. I don't know. I don't think that we were nearly as useful to those other communities as we had hoped we would be. And the only solution to that, in my humble opinion, is continued engagement and continued prioritization of those interactions. And that's not something that my organization is really set up to support. So, so perhaps a funding model that emphasizes this dessert portion of the meal across communities, maybe that would be useful. You know, I mentioned this indoor air quality, right? That was within the context of FIRE-X at some level. We had reached out to a scientist whose name I can't remember at Colorado State University, who is very actively trying to measure reactive oxygen species to make the connection to health impacts. And we were very enthusiastic about supporting those kinds of things. I don't think we got that. That was a measurement, right? So that was a measurement is much easier to include than a more nebulous kind of broad support for a community. Again, since our focus on my particular community of research scientists, our focus really very tightly on each contributing to these questions of processes, chemical processes, impacts of dilution and temperature changes as plumes rise, lofting, all of these kinds of things. I think it's very hard for us to kind of broaden our gaze to the much wider impacts, just like the ones that perhaps the large-scale air quality models are associated with, that perhaps are more relevant to some of those communities that are focused on health impacts and air quality. Yeah, so I don't think I'm terribly helpful. You're absolutely right. I'm not the right person, but I would say that, in my opinion, those interactions aren't prioritized by our organizations.
Yeah, I think we have time for one more question. Marcella?
Thank you for the presentation. I have a quick question. While the objectives were air quality intended, you also did measurements for cloud aerosol interaction, and those measurements sometimes tend to be very different, and the flight that you need to do are different, how they're have to. What are your take-home messages according to the complexity of the different measurements? If it's better in this case to narrow and say we are going to just do air quality and aerosol interaction, or just aerosol cloud interaction campaigns, or do you see more important to link everything and try to get little pieces through the campaign?
Thanks for that question. It's an interesting one, because a large part of the power of the DC-8 platform is the way that it's able to house a whole bunch of different instruments together to sample smoke and characterize it in every way imaginable. And the assumption is always that the more measurements you have, the stronger the constraints you have on what's going on. And I don't think that that's an assumption that's wrong, but I do think that that people are limited and they can only absorb so much. And so, although conceptually it's true that you have more constraints, it's much easier to do an analysis from the Twin Otter with one, ozone NOx instrument than it is to do one from the DC-8 with this huge amount of data. And so I think that there's a place for both approaches, the very kind of intense FIRE-X-AQ-esque approach, where we really loaded on everything we could from every length scale, every altitude, and tried to get as many walls up around all of these problems as we could. I think that's hugely valuable. And every time a question comes up in the future that people didn't consider, they still have that data set to go back and look at. It happens, all the time. Oh, what about this? Oh, well, we have this data set. We can look at that and see and evaluate. But if you have a very specific question you want to answer, I think that there's probably much more direct, small scale approaches that help you address that one question. Plume rise, we didn't really need to know all of the chemistry of the smoke, did we?
Okay, looks like our lunch will be off a little bit longer. Well, we have a question online, and I think we can fit that in. We eat fast.
Does that mean that I can ask my question orally?
Yes.
Go ahead.
Terrific. So I want to congratulate all of you people. You do beautiful science. But from my perspective, the science that you do is not as helpful as I'd like it to be. I'm one of those people that Dr. Schwartz referred to. I am not an atmospheric scientist. I am a physician epidemiologist who is interested in the effect that smoke has on health. And there are a lot of problems in doing that. Number one, there are only a few species for which we have much information about association between exposure and outcome. And we need help from our toxicologist colleagues to expand that and give us finer gradations. But more importantly, we need data at surface level. We need indoor versus outdoor measurements. They may well not be the same. Because if you don't get that, and or if you try to infer from overall measurements rather than measurements on the level of the individual, you can fall into something called the ecological fallacy, which I'm not going to describe, but it's a well-known epidemiologic problem. So for me, the bottom line is you do beautiful work, beautiful measurements, but you're not providing to people like me the data that we need to estimate the effect of smoke on populations. What can we do about it?
I think that's a question for the committee, right?
Yep.
Not for me.
It's for anybody.
You know, the answer is always money.
Yes, it is.
Stacy.
Yeah, no, John, thank you for that insight and perspective. Very much appreciate it. I think at this time, we do want to stay on time for our after lunch presentations. So I'm just suggesting we wrap things up and move us into the lunch break.
Okay, so I think that means we're done for the morning, and now we can take a break and eat and other things. Okay.
Thank you for giving me a moment to get on my soapbox.
Thank you, John.
Good.
Again, thank you to the all right. Thank you all. I hope everybody enjoyed the lunch break. We are going to go ahead and get started again with our next speaker, Emily Fisher. This will be the last presentation of today's open session. And then at 2 o'clock, we will adjourn for closed session. But again, I just want to remind folks that this is the first of our information gathering opportunities. And I invite those on the line to be in touch, to communicate with us. Let us know if you have suggestions for additional folks we need to be hearing from, or categories of people we need to be sure we hear from. This is certainly not the last opportunity to engage with us. So with that, Emily, I will turn it over to you to introduce yourself, and you can go ahead and share your screen.
All right. Hi, can you hear me all right?
We hear you well.
Okay, great. And does that give you the right view?
Right now, we are seeing the presenter view.
How about that?
Yep, that's it.
All right, great. Hi, everyone. My name is Emily Fisher. I'm a professor in the Department of Atmospheric Science at CSU. And I'm going to give you a little bit of information on the We Can campaign, which occurred in 2018. This was focused on wildfire smoke and evolution, and it involved a very large team, multi-institution. And I was the lead PI and the lead navigator and flight planner. So that's the perspective I'll bring today. I changed some of my slides a little bit after listening to some of the other presentations. So hopefully I don't repeat too much, but also give you the information you need for some questions and discussion. So We Can focused on 3 distinct objectives related to wildfire smoke: air quality, nutrient cycles, and then climate and weather. Nitrogen is central to the Bethune plume chemical evolution, and so that's why the focus was there, in addition to nitrogen deposition in ecosystems. The second focus was on the evolution of aerosol optical properties, with a focus on changing light availability. And the third focus was on cloud activation and chemistry in the wildfire plumes. So we outfitted the NSF NCAR C-130 with a very comprehensive payload with respect to these 3 objectives. So it was very comprehensive with respect to reactive nitrogen. There were a number of different aerosol measurements, and then we had measurements to collect cloud particles, understand which ones were active, and then so that we could understand microphysics and smoke impacted clouds. So I just popped this in for campaign planning. So when we were planning this campaign, and this is something that I want to emphasize sort of the difference between the aircraft versus the ground-based operations. So the pre-campaign planning started a year ahead, and that involved me and others doing pretty extensive briefings on the logistics of typical firefighting aircraft patterns. We worked with Stan Kubota, who also then worked with the FireX team in 2019, because that campaign followed the aircraft portion of that followed in 2019, who was a former burn boss and air tactical supervisor. And so he served as a liaison, and sort of my relationship with him and some of the other atmospheric chemists really helped us to co-design things. The NSF NCAR pilots did a bunch of professional development also in that year, and we did pretty extensive safety scoping and imagining different scenarios, including carbon monoxide in the cabin, altitude restraints, coordination with air traffic control, heat management, all sorts of things for the team. And the flight patterns were iterated so that they met safety and those 3 scientific goals. So we used the C-130, which is a large aircraft, to get into very fresh smoke. And to do this with a large aircraft, you need to have that smoke at a certain altitude to have flexibility, and you need to be out of the way of the firefighting team. So the aircraft was based in Boise that summer, which gives a really good range of where you can reach. And there were ground teams. And as I think about this, thinking back to look ahead, right? The aircraft can move very, very quickly and respond to an incident or a fire in any area, right? But the ground teams or ground-based measurements are moving very slowly, or might only be able to work in California or something like that. So as we look ahead, we might think about how to position so that a future campaign can work on multiple things at the same time, because it's very hard and very slow to get an aircraft in the air, but it can cover very large areas. So these are all the wildfire. If you remember, summer 2018 was an extremely active fire season, and that's a main difference between WECAN and FireX, is that they were just very large. And we sampled very large fires. So we sampled, for example, the Carr fire on the day that it was burning the town. So this is what it looked like. I'll just show you a quick video of what this looks like, and I'll put it over here. We were working, this is actually coming back from working on another fire, but we could see this fire, which was not being actively fought on the satellite images. And so like the very rapid communication between myself and Stan and an incident management teams figured out that this wasn't actively being fought. So we came up behind it on our way back, and then we just kind of crisscross in the most dense smoke. And this one, which wasn't being actively fought, gave a lot of flexibility for us to sample it many different ways at different altitudes and things like that. So I'll go ahead here. So WECAN focused on really large fires in the afternoon, and with, in retrospect, relatively high smoke injection heights, which was allowed for sampling. But this is also when really large increases in burn area were being made. And so we would often leave Boise at just before 1. I would sort of finalize flight plans that morning. I'd have 3 or 4 fire options open and filed as potential flight plans. Stan would communicate with incident management teams and think about and get some insight on which fires were likely to make a run that day, or which had been put out overnight or controlled overnight. And then we would go in the afternoon, so that I sort of met the fire with the aircraft when it was really going. And we would stay from somewhere around 2-3 p.m. until just before dark, and then fly home. We sampled very large fires with a variety of different ignitions across the West that summer. There's another campaign, and I forget actually if I emailed this as a recommendation. You might want to think about also looking into this campaign, which was BB Flux, that occurred that summer. And that was also funded by NSF, and that was conducted with the University of Wyoming King Air. We coordinated a couple flights with that team. They had a different approach. They had a very small payload of in situ measurements, and then they had some remote sensing measurements. So they were often flying underneath the plumes, and they were able to quantify a full emission flux, but of a very small set of species. And WECAN, on the other hand, was able to characterize very extensive composition, but not do a flux calculation. So from WECAN, we filled some pretty large knowledge gaps in chemical plume evolution. And so that is sort of the big step forward from WECAN, is getting samples in that 30-minute, in a, let's say, fire in the wild, or whatever the first term was that was used this morning, tiger in the wild, from approximately 30 minutes of aging. So very, very close to the updraft, as much as we could go safely, to about 4 hours of evolution. So, and that really did focus on a lot of these oxidant budgets close in, and how that mattered for chemical evolution downwind. Big findings from WECAN are how the particulate matter mass and light absorption evolve in these plumes. And so we have I think, a much better understanding of the chemical and physical evolution of the part of smoke that we see, and of the gas phase smoke that we don't necessarily see. The other thing, and Shuka mentioned this a little bit, is that these major atmospheric chemistry field programs necessitate instrument development, and then atmospheric chemistry teams will often move on to the next challenge. So, and this is an example of that. So during WECAN, it sort of necessitated that my team optimize an ammonia instrument, and now that can be leveraged for agricultural questions. And so I think to sort of continue and refine community around prescribed in wildfires, I don't think there needs to be motivation. The atmospheric chemists would be happy to continue working in this space, but it's hard to imagine us getting funding to do a campaign if it feels like we've already done a lot of that campaign, but we have a bunch of instrument development and techniques that are readily deployed and then can be used in other contexts. So one of the other things that we did, it was such an active fire season that year, and I'm happy that we were able to do this, is after I finished getting us to a target location and doing all our near source chemistry, then we had a LiDAR on the aircraft. And so I was able to look up and down and see where there was a smoke plume, and then ask for permission to fly back to Boise in that smoke plume. And so what that built was a library, you can think about it, of mixed age smoke covering large regions. And because of the extensive chemistry payload on it, we have a way to chemically fingerprint the age of that smoke using some of the volatile organic compound VOC measurements. And so we have now a library of not in smoke, young smoke, medium age smoke, older, and sort of oldest smoke, with a pretty well-known range of ages. We also went into the smoke-filled Central Valley, and we came in and out of Boise, and Boise got a lot of smoke that summer. So we were able to compare a pretty typical small city, Western urban airshed with and without smoke. And so from the WECAN data set, you can make some comparisons to other places as they get smoke. So here's an example, like Boise on a smoke-free day, DC on a smoke-free day, Boise on a smoke-filled day. You can't see the mountains. DC on a, one of the 2023 bad days. Around the US, we measure particulate matter. And so in Boise, we could see increases in things other than things that are routinely measured. So we measured our criteria air pollutants, right? Carbon monoxide, ozone, particulate matter. But we're also seeing increases in things like the hazardous air pollutants, acetaldehyde, formaldehyde, benzene, acrolein, things like that. So our team has started to try to bridge that health gap, but that's hard to do. So one of the ways that we're trying to do that is take the WECAN data and ratio that to PM2.5 and start calculating hazard indices related to increases in PM2.5. So we can have a common language or a tool to start to understand the potential health risks of different chemical mixtures. When we see large PM events, we can get an idea of what else might be in that soup when a city is impacted. So this is one way I think this identifies the type of compounds for toxicologists maybe to shine their light on, and also what else is people are being exposed to. The other focus of WECAN was on this cloud aerosol interactions, and that flight planning was very different than, I took the video out for time here, but basically what we did in these instances was I would go to a location, we would identify cloud formation on satellite, we would go under and sample the smoke, and then I would pop up into this layer here and take the aircraft and go cloud to cloud. That was hard. Many of the clouds are actually ice instead of water, and that made it hard to collect them. But what we did find is that the smoke particles do act as nuclei on which cloud droplets form. And so these smoke impacted clouds are very different than unimpacted clouds. The droplets are very small. They're about half the size of cloud droplets and are not influenced by smoke. That has pretty big implications for the atmosphere. Therefore, they reflect more light, and they may also produce less rain. So this was very technically very challenging, and we were able to do it about 5 times to get into these mixtures. This required no coordination with the incident management teams, but a lot of coordination with meteorologists and a lot of flexibility. It's very hard to identify flight altitudes and things like that for this kind of thing. So we can, and these in situ observations, which I can't overstress the importance of in situ observations for improving models and interpreting satellite observations. You really, really need that as you sort of look forward for tackling this problem holistically. But with the WECAN in situ observations, we were able to do a really update and I would say, I don't want to say revolutionize, that sounds like a little too extreme, but really update our near fire chemistry of smoke. We do understand that the cloud particles, which are impacted by smoke, which is on a large fire season, a lot of the clouds are quite a bit smaller than unimpacted clouds. We do have a pretty good understanding, and more work could be done here. There was no funding for this. This was done with a fellowship on the side, but how smoke is elevating the hazardous air pollutants, the gas phase hazardous air pollutants, along with PM 2.5. And then there was a lot of analytical development that occurred just because sampling smoke is hard. It's very, from a chemistry perspective, it's very concentrated. So, in addition to the publications, these are some capacity building that occurred during WECAN. So WECAN occurred ahead of Fire XAQ. That wasn't intentional. We meant to have them in the same year, but then for some, typical aircraft logistics, that campaign had to get moved. But we went ahead. And so we were able to test and develop the flight patterns and the safety protocols with the Forest Service. And I think that was a really important part of WECAN. Right now, there's the development of aerosol parameterizations within cloud and mesoscale models to account for the smoke. And then this is ongoing with the WECAN data. For some chemical transport models, the teams are working on understanding the missing chemical processes in those. WECAN also piloted best practices in preventing sexual harassment. We did a big public education campaign. So there is a set of videos and lesson plans that were actually developed. If you're thinking about how, ideas or examples for public education coming out of future efforts. So those might serve as nice examples to look at. We are working on better impact assessments by thinking about how you take the ratios of what was measured in WECAN to things that are routinely measured in our air monitoring networks, the networks that are used by epidemiologists. And then I mentioned this in email. I think it'd be great to talk to the NSF EPSCoR team in Montana, who they're working on prescribed fire. Specifically, I would talk to Lu Hu. And I just put some notes together to start questions here of things I heard this morning. I really do agree with this framing that a unified model of fire that crosses scales is needed. And I agree that we've made huge progress on the smoke chemistry and more on smoke transport, injection height distribution is what's needed for public health. In terms of immediate opportunities that I see, I don't know if this exists. I don't think so, but it would really help to have a consolidated system for recording US prescribed fire activity and a really thoughtful documentation of spectrum of intensities, conditions, fuel consumption for prescribed in wildfires. It would really help to take advantage of all the information that's already been collected and design campaigns where to hit very specific conditions where we have gaps. You could definitely use the wildfire sample during weekend and bbFlex for future modeling. That has been underdone, I think, just due to the way those campaigns were supported through atmospheric chemistry. The specific chemistry has been done, but not a lot of the more physical aspects of the plumes. I also wanted to mention that the methods, I think, are really ready for indoor versus outdoor smoke composition campaigns. So there was a major atmospheric chemistry campaign called HomeChem that was conducted. And so the methods for doing indoor air are from an atmospheric smoke composition would be there, and the methods are for outdoor. So it's tricky to think about how the logistics of that, but the methods I think are in place finally for that. Some challenges that I see, the statistics require large sample sizes. So we need more fires to cover the range. That was good in 2018, but it's hard to get the aircraft really low into different burning types. Where I find difficulty, and I think Chad can attest to this because we spent many time talking about it, these time scales are ranging very large. So the time is like seconds to a month for these fires, right? And the length is meters to continental for the smoke. So it's just these scales are problems. In terms of these disciplinary boundaries, I think our coursework is currently lacking for training people who can work across these disciplinary divides. And the other thing I would think about is looking forward is like the ground observations tend to be fixed to a location or two, and air operations plan very slowly, but once they're ready to go, move very quickly, and then are relatively short duration due to their expense. So thinking forward, balancing those two things, I think will be really important. All right, what do you have for questions for me?
Emily, thank you for your presentation. We'll look to the room for questions now.
Yes, thanks, Emily. Can you elaborate a little bit on how you determine the age of the fuel?
Sure. So there's two ways to do this, right? You could use a wind speed and a location of what was burning that day, and you could get you could get an age that way. That would be one thing, and we often do it that way and chemically. So chemically, fires emit thousands of different VOCs, and they have different lifetimes with reaction with the main atmospheric oxidant, which is OH. And so we're able to determine age by knowing that certain compounds were emitted and they are no longer there in the smoke. They are no longer detectable. So that tells us that the lifetime of that particular piece of air from emission to when we're that tells us that that's longer than the lifetime of that compound. So and we did that for many different sets of VOCs with different lifetimes. And so given measurement uncertainty, we were able to bin things pretty closely that way. So we could say that one's, less than a day, more than a day, less than a week, that kind of thing. And so the wind speed and fire location works really well if you're close to a fire. So in that case, but when you get further away, the chemical method is a little bit more reliable, I think, and easier to implement. And we're sampling these things largely outside of urban areas. And so we are sure we're in the plume and those species are from that fire. Does that help?
Yes, thank you.
No problem.
Rod?
Thanks, Emily. Great presentation. My impression from what from your description is even in the cases where you're just flying through plumes, there wasn't, you weren't taking advantage or maybe there was none available information about what was burning, how fast it was burning, and the details on the ground. It was, you were more interested in the evolution once it was airborne and aging. Is that correct?
Yes, and so the focus is the focus was on the chemical evolution, and that is what we were, when you write an NSF proposal, we are fully capable of doing with the resources that we have. We did work with folks from the Forest Service, and all the fires that were sampled during WECAN have information on the fuels that were consumed, an estimate of the fuels that were consumed on the days that we were there, and the fuel type. And so we didn't plan around that, but looking back, we have that cataloged, and we did, in one of the papers, or maybe actually two of the papers, try to compare that do the calculation of kilograms consumed to emission ratio measured from the aircraft to other more bottom-up type inventories. And so that comparison has been started, and more work could be done there. It's very noisy because we're sampling these plumes. The updraft has already, in these cases, right, you've got a dangerous, very dangerous, massive updraft, and I'm going just outside of it. It's very well mixed, right? So it is a very holistic view of a large area burning. And so, yes, we did that comparison. I can point you to that and give you examples of how that's done. And also the scales are very different here, right? I'm worried about ripping the aircraft wings off, how close we're getting, right? But it's very well mixed, right? Like, and it's very high and it's a mess, right? So yes, and that. It's hard with the large wildfires to make sense of it. And it also could be that the atmospheric chemists aren't looking at the right thing. We're just like, oh, okay, like they burned this in the flab and this had a lot of that. And this is what it looked like. So yeah, that's where that stands.
And on that flight path that we're designed to, purposefully picking up samples that might have been coming off of different parts of the fire, or are you in a position where everything is being sucked into one column pretty much?
Everything's being sucked into, yeah. Rod, can you just go closer to the mic? I might not have gotten your whole question, so if I don't answer it, then it's because I didn't hear the beginning. It is hard to do planning around that, but that also was not something I was asking Stan to help me with, right? I was more worried in 2018, given where we were in smoke chemistry, and something like this, you had never gotten really a large aircraft into a fresh wildfire smoke plume. And so I was more worried at that time, will that smoke be high enough in the atmosphere at 2 p.m. that I can get a large aircraft into it, rather than so I was looking for fires that were making large runs through whatever, basically. So I think you could do that better now with better communication and intentionality there, but we didn't do it then. At that point, I would be looking sort of overnight at which fires were really, big hotspots still going overnight on the satellite overpasses. Then Stan's calling incident management teams, knowing a general direction it's going to run, but that's irrelevant to me from the air, as long as I'm not interfering with operations. And then I was going into it. So we were looking at it after, and I think you could plan a little bit, but the issue you'd have to switch your aircraft probably to think about how you sampled these different, let's call it fire phases or times of day or different runs or whatever. A C-130 has to stay 1,000 to 2,000 feet above the nearest obstacle. And when you're in mountainous terrain, right? When you look over and you're like, that's Mount Shasta. I don't want to hit that. That's good that we're doing that, because you can't see when you're in the smoke. So, but you could go with a small aircraft and a large, you could be a little bit more flexible with a small and large aircraft. With a really large aircraft, you can't get that low. And so you do have to have a quickly rising plume. What else did I not answer, Rod? Because I didn't hear the beginning.
So I have a question. I'm over here. Was there any coordination with other agencies such as NASA as this was going on? Because I only asked because I'm aware that some of these fires were imaged. For example, the Carr fire was imaged with Avarice. I think the Taylor Creek fire may have been imaged with Neon ALP. So was there some coordination that happened while this was all going on, or was it just serendipitous because there were a lot of fires?
It was mostly, so WECAN and FireX were supposed to both go in 2018. So there was the start of coordination, and then FireX, which had funding more, it was a NASA NOAA supported mission, right? Went in 2019. So we did some serendipitous coordination, and there was coordination in that the people planning the next year's campaign came to learn how to flight plan with me in 2018. After I was, first couple fires figuring out how we were going to do this. So there was coordination there, but much of what happened with those multi ways of observing things is serendipitous, just because 2018 was so active, which is very different than 2019, right? 2019 was a bit unlucky in that it was a more assets deployed, but a less active fire season. I did try to do, some spirals, but it's very hard we were flying usually around 1:30 in the afternoon, right? So we were in line with A-Train, but again, this coordination was not particularly organized in that way.
Morgan?
Thanks for your presentation. That was really cool. I in particular like your emphasis on next generation and capacity. Capacity is something that we overlook with funding often, like we want you to do this. That sounds like a great idea. Go for it. Instead of we're building tremendous capacity that will long outlive the 2, 3, or 4 year project that you're conducting. And you kind of touched on it also, that there was a lack of sort of a pipeline for, the educational opportunities and how we prepare future scientists to do that. Anyway, I like that part a lot, and I like that you emphasized it, because it does seem like from the funder standpoint, that's an investment that you're making, is not just in the moment. And I know they know that, but it's cool to hear. The other part that was intriguing is that a lot of stuff happened quickly, and I think you made that point nicely. And from an instrumentation advancement standpoint, you talked about a single year that was 7 years ago. If you were doing this now, what is it? What sort of advances have occurred since then, and that occurred sort of on the fly during that period? If you can just sort of, give a take on that. That part seems pretty interesting. You were sort of having misses and learning as you were doing. Anyway.
Yeah. So one thing that made WECAN so successful was, and just to touch on the capacity building, was everyone that had not flown before, every instrument and every human that had not flown before, and those are two very important different components, tested their stuff 9 months ahead. And that was why the campaign data the quality is so high. We flew everything on the aircraft, mocked the upload, and did test flights way before you would typically do that for a field program. And that gave the new postdocs, the new grad students, knew what was going to happen, the pace at which things were going, and found the problems, which there always are. The way I would think about instrumentation from an atmospheric chemistry's perspective is we want things to get smaller and faster, right? That allows us to be more nimble on the platform of choice. And as some things get smaller, and smaller can be size and power usage and weight. So those are 3 different things: physical size, power, and weight. As some things get smaller, it allows for either additional instrumentation to be deployed alongside it, or something which needs to be more precise or faster to get slightly larger. And so there have been some advances in things getting smaller. And I think the way to think about that is it enables other things to come in. When we were filling up the C-130, I filled every inch of that because it's so expensive to get it in the air. So getting as many people and as much stuff on as possible. Now I think maybe we would not have to necessarily duplicate some measurements. So I also duplicated things that, like carbon monoxide, got duplicated because I was like, we can do nothing without this. So we need to make sure this works. So I think now we feel confident in some of these things that we don't have to duplicate, and therefore you could fit other things in. So that's sort of the way I would think about it more holistically. And then you know, we are now, my team's, just as a personal perspective, working with CRIS measurements and using the WECAN data set and processing, working with JPL to, you know, specially process different CRIS observations. That's been really great. Thankfully, we had those measurements on the plane. And so it's now offering us the way to understand how to interpret those satellite measurements better in smoke impacted environments. But it wasn't planned, right? The in situ measurements were there. And from my brain, it was not planned that way.
Okay.
Hi, Emily.
Hi there. I can't hear you.
When I look at the website, I see the data is shared, and in a way it could be downloaded. Was there other challenges related to getting the data used by others in terms of the publications they led to, or? And the secondary part of that question is, NSF and NOAA are different types of agencies that this was funded through. So was there an impact expectation from different perspectives that you had to do something about differently? You know, NSF's mission being different than NOAA's in terms of practical versus research, for instance, expectations. Did you have to do something special to balance between the agencies?
So the answer to your second question is probably no, because I feel NSF is so fundamental science focused that felt pretty flexible to me. Where I felt pressure, honestly, was to move the campaign to 2019. That was very stressful for me to decide to stay in 2018. But with the big group of trainees that had already been hired at that time, I felt like I couldn't delay that for them. So that's where I felt pressure, not scientifically what to do. It was to move and go along with the other agencies. And that was a very difficult decision to go in 2018. In the end, it worked out great. That was the big fire year, and everything worked out well. So that's where I felt some real stress at the time. And your first question, can you just say it one more time? That was where your mic was cutting out a little bit. I can't hear her. Can maybe somebody repeat or something? It's weird. Like when you lean over, I can see you lean over and talk, but I can't hear it. That's better.
You can hear me okay?
Yes, good.
All right. I think what Ilke was asking is if there have been any challenges to getting the data used by others and tracking how and where that's been done.
Okay, so I don't think there's challenges within the smoke chemistry community or atmospheric chemistry community. There's been 50 publications or something like that. It's a lot. I have trouble keeping track sometimes because I'm not really a tracker. That's a personal problem. I think one could do a better job at that. I think where it's really difficult is to have this data used by health scientists. That's where it's really hard for me to, we've only been able to start that a little bit with epidemiologists that I work with here on a day-to-day basis, where we're working on other projects, right? Because it's very hard to take all those steps of now make a national map that's gridded, that has PM 2.5 plus all these other things as an approximate amount with a lot of uncertainty. How do you use that appropriately? So I think the WECAN data set is really valuable, and it hasn't been sufficiently leveraged for health. That is where, but I think it has. And the other piece of the data set that has not sufficiently been leveraged is the cloud sampling. That is also something we anticipated. Sue Vandenhever, this is just a people issue, I think. Like Sue Vandenhever was the PI on that. It was chopped to the very small amount at the very end of the proposal, right? And then now she's, working on INCUS. So there's like that piece of the data set, I think, has enormous potential, but was not really funded. And I haven't pursued extra funding for it either. So those are the two things. I would say the gas phase chemistry is, really been well leveraged.
Kevin?
Thanks, Emily. I'll try to talk into the mic. How much was the total cost, and what component had the biggest return on investment, and which component the least? And for least, what was the driving factor there?
That's hard for me to say because I don't see the full set of costs with NSF proposals. So the piece that went to the what we would call the science teams was $3.8 million spread across all those 6 institutions. The aircraft deployment costs, I don't know. My guess would be, based on doing other budgets that I'm working on with other aircraft, my guess would be somewhere around $1.6 million, which I know is kind of specific, but I'm just guessing in 2018. And I don't know, I would guess it's like in that range for all the stuff. But it might be less than that, actually. It's just, that's hard for me to know. But I think we could easily get that funding from NSF. It's very hard for me to separate what is a low return on investment, because I feel was pretty well coordinated. The highest risk was always the clouds. That was always the risky part. It was not a high cost. We did a small amount of the flight hours on it, and the rest was required to interpret the data. Right, it was a coherent package that you really couldn't have had a good understanding of the near phase chemistry without. I'll tell you what was a really good investment was the contract with Stan. That was an extremely high return on investment. So I can say positive. Is that helpful? At least like the Stan coordination was absolutely essential. And the pilot training so that they were comfortable in that environment. And they could problem solve with me on the fly. That was, so I could say, hey guys, can we do this? And they'd be like, oh yeah, I think that's fine, right? Like, so they just a really good understanding, and the pilot feeling comfortable in the NSF NCAR pilots feeling comfortable in that environment, and knowing where the firefighting teams likely were and where we were operating. Those investments, I think, were really important.
Aaron?
Hi, Emily. I have a quick question just about from the aircraft perspective and the malleability. So we know last year the DC-8 from NASA was retired, and they have a new 777, which is a very large aircraft. Would you be able to speak to the current and even future potential field campaigns and the importance of these aircraft as laboratories, as flying laboratories, and this malleability as, for fire, small aircraft, high aircraft, large aircraft? Are there impediments? Is there an ease of access with smaller? Could you speak a little bit to that about these flying laboratories?
Yeah, sure. So it's very, very important that you have access to these flying laboratories because they can respond. And fire, right? Unless you light it yourself, you really don't know where it's going to be. And so even moving around a fire, right? Like the aircraft are very, very flexible. So to fully study this phenomena, I do think you need tiers of aircraft. So a smaller aircraft like a King Air, I'm assuming everyone in the room is familiar with sizes of aircraft. So a King Air is typically like, 6 to 8 seater. That you rip the seats out and fill it with instrumentation. You can get waivers for a King Air to fly relatively low. So for example, here under flat ground in Colorado, I've brought a King Air down to about 300 feet. That's low, not meters, above ground safely, and done sampling. In these environments, they were able to take the King Air down to about 500 feet above ground. So that gives you a lot of flexibility to go under a smoke plume, not in it, right? And it allows you, which lets you get if you're looking up at the sun and doing a column estimate, emission flux of things, it also gives you a lot more flexibility flying in these little valleys. There are real issues flying at night that are scary for people and pilots. And so that's hard, but Shuka FireX did some of that with a Twin Otter. There's ways to do it with missed approaches and things like that. But so small aircraft is flexible and can fly at lower altitudes. The benefit of something like a King Air, like a C-130, like a P3, something that those sizes, is that you can be much more comprehensive. It also allows for more training, right? So it allows for some redundancy, which is really important. It allows for a more complete payload, and that complete payload can be humans. And so that helps with your navigation and your communication and also the instrumentation. And it also flies, compared to like a G5 or something like that, lower and slower, and which is important for instruments that have a physical time from getting something outside in and actually sampling, right? So you whip through something too quick and you're actually not able to sample it very well. So there's an advantage to not be the fastest always with an aircraft, to be in the air, but not the fastest in the air. So doing that sort of mid-range of altitudes from 1,000 feet above ground level to like 20,000 feet, something like that. And then I think, as you know, we look ahead to mega fires and things punching up really high, you do need the higher aircraft that can operate at higher altitudes. And I think the same thing goes for the instrumentation, right? You need instruments that can be operated without humans most of the time on the small, low-flying aircraft, and the higher, what can be kind of smaller aircraft like a G5 or something. And then you need instruments that can sort of operate manned or unmanned, right, in those different environments. Does that help lay out where I'd see? So I think to tackle these problems, right, you do need a range. You would like a range of aircraft, and they each have advantages. But you could also, Aaron, you could imagine you could do something quite similar to what we did with the C-130. If you had both a Twin Otter or two Twin Otters, or two King Airs, you could multiply the small aircraft to do a little bit what you could do with the C-130, or a P3, not quite as good, but you could get away with that too, I think.
Thanks, Emily.
More questions?
What about using unmanned things? 'Cause like larger drones or some things, you got Department of Defense here too.
So in 2018, my understanding was with the firefighting teams, they did not really want anything unmanned in those airspaces. So that was step one. They were actually quite relieved that there would be pilots and people and communication. And so there's that issue. And then the second issue is that many of the compounds we would want to measure in smoke, the instrumentation is not small enough, low power enough to be like used on those platforms, period. At the same time, I don't want to sound too negative, because I actually think there's like huge potential here in maybe even smaller prescribed fires. So a student of mine actually just made a whole table of instrumentation and uncertainty and precision of sort of what I would call lower cost, lower weight, lower power instruments. And I think there's potential there. There's a lot to balance, though, as I see it, sort of logistics of flying those things and the amount of time they can be in the air versus making measurements in batteries. I think there's quite a few logistics there to work out, but I think it's very possible. And there's been some recent papers that have used drones or dragged inlets up or done things like that. And so I think that there's neat, but there's issues.
More
But I don't want to
questions?
sound, I don't want to sound negative because I actually think there's quite a bit that could be done if that was well thought out.
No, I don't know if we have more questions.
Emily, thank you very much. There are no additional questions in the room. I'll offer for those on the line, if there are any questions from the audience, we can take one or two of those now. Otherwise, we can also close our open session a little bit early. So I'll maybe wait just a few seconds to see if anybody online decides to raise their hand as well.
Looks like we're heading out a little early, not totally. We have to come back, of course.
Emily, thank you very much for the presentation. And I just want to thank again all of those who have joined us both in the room and also online for our first open session of this committee. We will be solidifying additional meeting dates and open meeting sessions. Some of those probably today or at least this week. And those will be posted on our website. But if you have any questions in the meantime, please don't hesitate to be in touch with me at any point. With that, I think we can adjourn our open session.
Hey, Stacy, can I just
Please.
say a quick thank you to everyone? Just as from one of the sponsoring agencies, just wanted to thank the speakers online. Thank you all for your inputs, your invaluable inputs. The public, also the committee for, asking the good questions, especially for us as sponsors yesterday. I know hopefully we'll get in the future, some of those questions will be funneled through Stacy to us as you need clarification. And wanted to close out on some of the things, just kind of clearing up. I know that this is the last time for public until next time. But just a few quick things, just kind of tightening up, if I may, is considering just some of the discussions that came about today that maybe weren't highlighted yesterday were things like data management and the life cycle of data. There have been also a life cycle or different iterations of data management systems, such as the Forest Service Research Data Archive. There's also the WFC, which we talked about, that was discussed today. There's also the NASA's, their Distributed Active Archive Centers, or DACs. NSF has some of their own that I think there are some archives within the National Center for Atmospheric Research. Just thinking about data management and the life cycle there, that would be within the confines or within the scope of this study. Other things are thinking about considering the lanes. One of the things I brought up yesterday, especially with agencies, multiple agencies with various missions, this was brought up today, even within agencies. So within the Forest Service, for instance, there's a lot of focus on fire and aviation management, a different deputy area within the Forest Service that we hear about in the news. There's a big focus on suppression. And other parts of the agency may have more ties to management of the land. But then also there's a prescribed fire component, especially within research and development. And just thinking about, the different missions in the mission spaces, interagency, but also intra-agency. And then other areas, I was hearing some communications afterwards once the data is collected, et cetera. There are some swim lanes, especially as other agencies and entities get involved in prescribed fires. Thinking about, communications with, Joint Fire Science Program. They have their fire science exchange networks that are, connecting science to managers on the ground, and their graduate research program, the GRIN. That is something we're connecting, getting students involved. So those are all, things, maybe some agencies or entities that are within the federal landscape or programs that are not actually agencies themselves could be considered. And the last thing is, as you go through and, consider this study and your deliberations, thinking about, there was a discussion on building on capacity. From an agency perspective, I would be looking to this committee for advice and recommendations on, if I had an extra $1 to $2 million, where am I going to put my investments? If I had $200,000, where would I put these investments? This is to balance the advancements in fire and smoke science, but also for management and operations. So there are a lot of things that we have to consider at our agencies. And so I would really, at least from this agency perspective, really appreciates that advice and recommendations on where would we put this extra dollar if we had one? Or to the same token, if we had to remove a dollar, where would we remove that from? And so I'd be looking for this report to help with those recommendations. Anyway, with that, thank you all.
Aaron, can I ask for a clarification real quick?
Sure.
So I assume we're still talking about under the, I mean, you're talking about if you had $200,000, you're still talking about within the sort of prescribed fire science or observations to support prescribed fire science umbrella.
Yes,
That's correct.
sorry. Yep, all within this umbrella. Yep, thank you. Thanks for that clarification, Rod. Yes.
Fantastic. Any other questions, comments before we adjourn? All right. Thank you each. We, committee can take maybe 10 minutes. That's all right. And we can reconvene. We'll say 8 minutes at 2:05.